Welcome back to QHSE Talks. Usually when we think about workplace safety, we tend to visualize these like static defenses.
Right, like putting up a guardrail to stop a fall.
Exactly, or applying a lockout tag to stop a machine. I mean, it's a physical barrier. You just install it, it sits there, and you completely trust it to do its job.
Yeah, it's entirely passive, like a wall just waiting for an impact, which honestly works perfectly fine for kinetic hazards, like gravity or a moving gear.
Right, but when you step into the world of fire protection engineering, suddenly that static wall is just, well, it's painfully inadequate.
Oh, absolutely.
Because if you're preparing for your ASP or CSP exam right now, or if you're just out in the field managing a complex facility, you realize pretty quickly that fire doesn't behave like a falling object.
No, not at all. It breathes, it grows exponentially, it actively consumes its environment.
Yeah, so the defensive landscape we have to build against it has to be active too, right? Yeah. It has to constantly sense an anomaly and then adapt to the specific chemistry of the environment.
Exactly, and then deploy this highly targeted dynamic response to neutralize the threat before it takes over the entire facility.
It's fascinating. And that perfect matching of threat to response is the primary mission of today's QHSE Talks. We are dedicating this entirely to Domain 4, Topic 7 of the ASP and CSP exam blueprint, Understanding Fire Suppression Systems.
It's a huge topic.
It really is. So for you listening, whether you're an ambitious safety professional grinding through your exam prep and trying to secure a rock-solid grasp on this, 10.66% chunk of the blueprint, or you're just a seasoned practitioner looking to audit your own facility's defenses, this is for you.
Yeah, because this isn't just about memorizing a table of facts for multiple choice tests. We're talking about mastering an essential life safety skill.
Right. Knowing this material is literally how you perform your duty and protect lives.
Well, the exam blueprint provides the framework, but the ultimate goal is practical application. Like when the absolute worst case scenario unfolds, the systems you oversee have to function exactly as designed. Because the life safety of workers is a legal obligation, sure, but fundamentally it's a moral one.
I completely agree. So to get us into the mechanics of how we actually do that, we've pulled from a massive stack of authoritative sources for this QHSE Talks. We're synthesizing the Board of Certified Safety Professionals, or BCSP, exam blueprints.
Right.
We're pulling from advanced fire protection engineering manuals from the NFPA. We're also digging into the highly rigorous OSHA 1910.119 process safety management standards.
Which can be dense, but so important.
Oh, incredibly dense. And finally, we're incorporating specific test prep materials, like the Bowen EHS question bank.
So we have a lot of ground to cover. We're going to start at the microscopic level, the fundamental science of combustion.
Right.
From there, we'll scale up to massive automated water systems, then look at specialized chemical systems, and finally break down the frontline manual defenses and maintenance protocols.
Perfect. I want to start right at that molecular level. Because before we can even begin to talk about suppressing a fire, we have to establish what a fire physically is.
It's crucial, yeah.
If we go back to basic chemistry, the foundation is the fire triangle, which most of us know: heat, fuel, oxygen.
Right, but more accurately, it's the fire tetrahedron.
Okay, the tetrahedron. Walk me through that.
Well, the classical fire triangle, heat, fuel, oxygen, was the standard model for decades. You remove one, the fire goes out. But fire science evolved because that model didn't actually explain everything.
What do you mean? What was missing?
It didn't explain why certain chemical extinguishing agents worked so incredibly well without necessarily removing heat or oxygen.
Oh, interesting.
Yeah, so that led to the recognition of a fourth critical component, the uninhibited chemical chain reaction. Add that fourth element and the triangle becomes the fire tetrahedron.
I want to pause on that fourth element because heat, fuel, and oxygen are intuitive. I can hold a piece of wood, I can feel heat, I can breathe oxygen. But what exactly is the chemical chain reaction?
It's a bit abstract, I know.
Like if I'm an exam candidate, how deep into the chemistry do I actually need to go here?
You don't need a PhD in thermodynamics, I promise. But you do need to understand the mechanism. Inside a flame, you have self-sustained chemical reactions occurring constantly.
Oh.
When fuel gets hot enough, it vaporizes. Those vapors mix with oxygen. But for them to actually burn, the molecules have to break apart and recombine.
Recombine into what? Like smoke?
Yeah, into byproducts like carbon monoxide, carbon dioxide, water vapor, and free carbon, which is the smoke we see. But the critical intermediary step, the engine driving it, relies on the creation of free radicals.
Free radical.
Specifically, the hydroxyl radical. It's an oxygen atom bonded to a hydrogen atom, but it has an unpaired electron.
Meaning it's highly reactive.
Wildly reactive. It violently rips apart other fuel molecules, creating more heat and more free radicals, which just rip apart more molecules.
So it's runaway chain reaction.
Exactly. If you can introduce an agent that bonds with or neutralizes that hydroxyl radical, the fire literally cannot sustain itself. The reaction stops instantly.
Even if the fuel, the heat, and the oxygen are all still sitting right there in the room.
Even then, the fire just dies.
Wow. Okay. So if we look at the entire fire suppression philosophy, it's basically like trying to kick a leg out from under a four-legged chair.
I love that analogy.
You take away heat, you take away oxygen, you take away fuel, or you break that chemical chain reaction, and the whole thing just collapses.
That is the perfect functional analog. Extinguishment is simply the physical or chemical process of removing one or more of those four legs.
And how you choose to kick that leg out depends entirely on the specific class of the fire.
Exactly. Which brings us to the classification system.
Let's walk through these because they dictate pretty much every engineering decision in a facility. We've got Class A, B, C, and D. Let's start with Class A.
Class A fires involve ordinary combustibles, so wood, paper, cloth, rubber, plastics.
Basically, the fires you typically see in a standard office building or like a cardboard packaging facility.
Right. And the primary method for kicking the leg out from under a Class A fire is cooling. You want to absorb the heat and drop the temperature of the fuel below its ignition point.
Which is why water is the undisputed champion for Class A.
Absolutely.
But let's dig into the physics of why water works so well. Because it isn't just because water is cold, right?
No, it's actually about thermodynamics, specifically the latent heat of vaporization.
Okay, break that down.
Well, water has an incredibly high specific heat capacity, meaning it can absorb a massive amount of thermal energy just to raise its temperature. But the real magic happens when water reaches 212 degrees Fahrenheit and boils.
When it turns to steam.
Right. Through that change of state from a liquid to a vapor, water absorbs a truly massive amount of heat energy from the surrounding fire. And furthermore, when water turns to steam, it expands roughly 1,700 times its original volume.
Wait, 1,700 times? Are you serious?
Yeah, it's huge. 1 gallon of liquid water turns into about 1,700 gallons of steam.
That's insane.
So that massive cloud of steam physically displaces the oxygen surrounding the fuel. So water primarily cools, but it also provides the secondary smothering effect.
That is fascinating. Okay, so water is attacking the heat leg and partially the oxygen leg. Now, let's move to Class B fires.
Yeah.
Because this is where the physics of water suddenly becomes a huge liability.
Oh, a massive liability.
Class B involves flammable and combustible liquids and gases, right? Like gasoline, alcohols, propane, grease.
Yeah. If you throw water on a grease fire or a pool of burning gasoline, you're going to have a catastrophe.
Because water and oil don't mix.
Well, it's a combination of density and that expansion ratio we just talked about.
Correct.
Water is denser or heavier than most flammable liquids. So if you spray a solid stream of water onto, say, a vat of burning oil, the heavier water instantly sinks straight through the burning oil to the bottom of the vat.
Right.
But the oil at the top might be 500 degrees. So the water hits the bottom, instantly boils into steam, and expands 1,700 times in volume in a fraction of a second.
Oh, wow. So it effectively creates a steam explosion at the bottom of the tank.
Exactly. It violently erupts upward, blowing that 500-degree burning oil out of the vat and spraying it in all directions.
You've basically just taken a localized fire and spread it across the entire room.
Yes, it's a nightmare. Therefore, for Class B, you cannot rely on cooling with water. You need to inhibit the release of combustible vapors or reduce the oxygen concentration using specialized foams or dry chemicals.
Okay, moving on to Class C, energized electrical equipment.
The operative word there being energized.
Right, because the hazard profile here isn't just the fire, it's the electricity. Class C fires require strictly non-conductive extinguishing agents.
Precisely. Because pure water is actually an insulator, but water in the real world is full of dissolved minerals and salts, which makes it highly conductive.
So if you use water on a live 4-volt electrical panel,
the person holding the hose or the extinguisher is acting as the ground. The current travels straight back up the stream of water into the human body. It's a severe electrocution hazard.
So we rely on dry chemicals and clean agent gases. But I've read that once the equipment is de-energized, like say you flip the main breaker to that panel, the fire is technically no longer a Class C fire. Is that true?
That is correct from a strict classification standpoint. Electricity itself doesn't burn. What's burning is the plastic insulation around the wires.
Right, the fuel.
So once the power is definitively cut, it reverts to a Class A or Class B fire. However, during the chaotic, incipient stage of a fire, it is incredibly dangerous to assume the power is fully isolated.
Because the breaker might have failed.
Exactly. You always treat it as Class C until it's proven de-energized through proper lockout-tagout procedures.
That makes total sense. You don't want to bet your life on a faulty breaker. Finally, we have Class D fires. Combustible metals.
Magnesium, sodium, titanium, potassium, you see these in specialized manufacturing or aerospace, and these are incredibly intense, high-temperature fires.
And you absolutely cannot use water here either. Is it the steam explosion issue again?
Actually, it's much worse. Water reacts chemically and explosively with burning combustible metals.
Like chemically?
Yeah. Burning magnesium, for example, burns at over 5,000 degrees Fahrenheit. It is so intensely hot that it will literally rip the oxygen atoms right out of the H2O water molecules to fuel its own combustion.
It uses the water as an oxygen source. That's terrifying.
It is. And when it strips the oxygen from H2O, what is left? Hydrogen gas.
Which is highly explosive.
Exactly. So by putting water on a magnesium fire, you're feeding it oxygen and simultaneously generating a massive cloud of explosive hydrogen gas.
That sounds like a complete nightmare for a safety engineer.
Yeah.
How do you stop something that literally feeds on water?
You have to use special extinguishing agents specifically rated for the metal involved, mostly proprietary dry powder agents, and note that it's dry powder, not dry chemical, which is for B and C.
Huh, good distinction.
Yeah. There are also some non-proprietary agents like completely dry sand or sodium chloride. They work by completely encasing the burning metal, isolating it from oxygen, and acting as a massive heat sink.
So if I'm taking the ASP or CSP exam, how tricky do they get with these classifications? Am I just memorizing Class D as metals, or do I need to know these specific chemical interactions?
You absolutely need to understand the mechanism of extinguishment, the why.
Okay, give me an example.
If an exam question describes a machine shop where workers are turning titanium parts on a lathe and a fire starts in the shavings, the candidate must immediately identify it as a Class D hazard.
Right.
They need to recognize that activating a standard water extinguisher would cause an explosion. They need to know why a dry powder is required.
So it's about applying the knowledge, not just rote memorization.
Exactly.
Okay, so knowing what puts out a fire is step one. But before we can deploy an agent, the facility has to actually detect the fire. The sources mention that fire protection engineering is fundamentally a war against time. We have heat detectors, smoke detectors, flame detectors. How does this sensory network actually function?
Well, you have to match the sensor to the expected hazard profile of the room. In the vast majority of standard commercial fires, there's a significant smoldering phase that produces smoke long before there's enough thermal energy to trigger a heat detector.
So smoke detectors are your primary early warning system.
Yes.
And there are two main types of smoke detectors that the exams focus on: ionization and photoelectric. Let's start with ionization. I know they work differently, but can you break down the actual physics?
Sure. Ionization detectors are fascinating. Inside the detector, there's a tiny detection chamber. And inside that chamber is an incredibly small amount of radioactive material, usually americium-241.
Wait, radioactive material like in a standard smoke detector?
Yeah. It's completely safe, but it emits alpha particles which constantly bombard the nitrogen and oxygen molecules in the air inside the chamber.
Bombarding them how?
It literally knocks electrons off the air molecules, turning them into positive ions, while the freed electrons attach to other molecules to make negative ions.
Okay, so the air becomes charged.
Exactly. Because you now have charged particles floating in the air itself becomes electrically conductive. The detector runs a tiny, continuous electrical current across this ionized air.
So it's basically a complete circuit using the air as a wire.
That's a great way to put it. Now, when a fast-flaming fire starts, like a paper fire, it produces very small, almost invisible particles of combustion.
And those particles enter the chamber.
Right. When those microscopic smoke particles enter, the ions attach themselves to the smoke particles. Because the smoke particles are much larger and heavier than air molecules, they don't move as fast, which interrupts the flow of the electrical current.
The detector senses the drop in current and triggers the alarm.
You got it. So ionization is highly sensitive to the tiny invisible particles produced by fast-flaming fires.
So what about photoelectric? That's the other type.
Photoelectric detectors rely on optics, specifically something called the Tyndall effect. Inside the chamber, there's a small light source, usually an LED, shooting a beam of light in a straight line. Off to the side, in the dark, is a light sensor.
So under normal conditions, the light just shoots straight past the sensor.
Exactly. But when visible smoke particles enter the chamber, they physically get in the way of the light beam.
Oh, and they scatter the light.
Yes. They scatter and reflect the light in all directions, including onto the sensor that was previously in the dark. Once the sensor detects that scattered light, it trips the alarm.
That's brilliant. So one is for invisible particles, one is for visible.
Right. Photoelectric detectors are much better at detecting slow, smoldering fires like a cigarette in a couch cushion, because those fires produce larger, highly visible smoke particles.
Okay, so if smoke detectors are so good, why do we use heat detectors at all?
Because smoke detectors are prone to false alarms in specific environments. If you put an ionization or photoelectric detector in a commercial kitchen or a dusty woodworking shop, they will go off constantly.
Because the dust or steam mimics smoke.
Exactly. In those environments, you have to use heat detectors. They're slower to react, but they are highly reliable and much less prone to false alarms.
And there are two main categories of heat detectors: fixed temperature and rate of rise.
Yes. A fixed temperature detector operates when the ambient temperature reaches a specific point, say 135 degrees Fahrenheit. It doesn't care how long it takes to get there.
But wait, if I have a massive warehouse with really high ceilings, a fire might have to get dangerously large before the ceiling temperature hits 135 degrees, right?
Yeah, and that is the inherent weakness of fixed temperature detectors. They suffer from something called thermal lag. By the time the metal inside the detector actually absorbs enough heat to reach 135 degrees, the air around it might already be 160 degrees, and the fire below is huge.
So how do we solve thermal lag?
That's where the rate of rise detector comes in. It doesn't look at the absolute temperature, it looks at the speed of the temperature change.
So it's looking for a sudden spike.
Right. It usually contains a small air chamber with a flexible metal diaphragm. Normally, as the room slowly warms up and cools down, a tiny bleed hole lets the pressure equalize. But if a fire flashes, the temperature spikes rapidly.
And the air expands too fast for the bleed hole.
Exactly. The pressure builds up instantly, pushes the diaphragm up, completes the circuit, and sounds the alarm.
So if someone opens an industrial oven door, the absolute temperature might not reach the 135-degree fixed limit, but a sudden flash fire from a chemical spill would instantly trigger the rate of rise.
Precisely. And finally, we have flame detectors. These activate in response to radiant energy, specifically ultraviolet or infrared light generated directly by the combustion process.
They're literally just looking for the light signature of a flame.
Yes. And these are incredibly fast. They don't have to wait for heat to rise or smoke to drift. They operate at the speed of light.
You'd use these in high-hazard areas, I assume.
Yeah, petroleum loading racks, aircraft hangars, places where a fire will flash instantly across a massive pool of fuel without a long, smoldering phase.
Okay, so the facility's sensory network has detected the fire. The system knows something is burning. Now, let's explore how we deliver the extinguishing agent automatically on a massive scale.
The heavy artillery.
Exactly. Let's look at water-based automatic sprinkler systems. The sources describe these as the absolute workhorses of facility fire suppression.
They really are. Decades of data prove they're the single most effective means for controlling fires in buildings. But it is crucial to understand their primary design goal.
Which is?
Unless it's a highly specialized system, a standard sprinkler system is not necessarily designed to completely extinguish a massive fire. Its primary goal is to control a fire in its incipient stage.
Incipient stage. That is a phrase that pops up everywhere in the safety literature and on the exams. Can you define exactly what that physical state is?
The incipient stage is the very beginning phase of a fire. There's ample fuel and ample oxygen available. The fire is producing some heat and smoke, but it hasn't transitioned into a free burning state or reached flashover where every combustible surface in the room ignites.
And from a human safety perspective, how do we define it?
OSHA defines it based on human intervention. It's when a fire can still be safely controlled or extinguished by a worker using a portable extinguisher, without needing specialized protective clothing or breathing apparatus.
So once you had to back away because the heat is too intense, it's past the incipient stage.
Exactly. Sprinklers are designed to catch it right at that specific window, holding it in check until the professional fire brigade arrives.
So how exactly does a standard sprinkler head operate? Because I think the general public assumes that if someone pulls a fire alarm in a hallway, every single sprinkler in the entire building turns on at once, ruining everyone's day. like in the movies.
Oh, that is probably the most pervasive myth in fire safety.
It's just Hollywood magic.
Completely. In the vast majority of commercial systems, sprinkler heads operate completely independently of one another. A standard sprinkler head is basically a brass plug holding back highly pressurized water. That plug is held in place by a thermal sensor.
And what does that thermal sensor look like mechanically?
The most common modern type is the frangible glass bulb. It's a tiny, heat-sensitive glass vial. Inside the glass bulb is a liquid, usually a glycerin-based solution, and a tiny air bubble.
Oh, I've seen those. They're usually red or green glass tubes.
Yes. When a fire starts below, the hot gases rise and heat the glass bulb. As the glycerin solution heats up, it expands.
And it compresses that tiny air bubble.
Right. Once the air bubble is fully compressed, the expanding liquid has nowhere else to go. The internal pressure shatters the glass bulb.
Right.
With the bulb gone, the plug drops out and the pressurized water hits a deflector plate, spraying over the fire.
That is incredibly elegant physics.
Yeah.
Just fluid expansion, breaking glass. What's the other type?
The fusible link. It uses two small pieces of metal held together by a special solder alloy engineered to melt at a highly specific temperature. When it melts, the plug falls away.
But the key here is that the heat physically breaks the mechanism on that one specific sprinkler head.
Exactly. The fire alarm down the hall has absolutely no physical connection to the sprinkler head.
You mentioned the specific temperature. The sprinkler heads are color-coded based on that activation temperature, correct? This seems like prime material for an exam question.
Oh, it's highly testable. Safety professionals must know them. An uncolored or black frame or an orange or red glass bulb indicates an ordinary temperature rating of 135 to 170 degrees Fahrenheit.
Okay, that's standard.
Right. A white frame or yellow or green bulb is 175 to 225 degrees. Blue is 250 to 300. Red frames or purple bulbs are 325 to 385, and green frames or black bulbs are for extremely high temperatures, 400 to 475 degrees.
Let me stop you there. Why on earth would you ever install a sprinkler head that doesn't activate until the ceiling reaches 475 degrees? Wouldn't the building be a total loss long before that opens?
You have to view it through the lens of ambient operating environments. Imagine you're the safety manager for a steel foundry or a commercial bakery.
Oh, I see.
If you install a standard 135-degree sprinkler head directly above a blast furnace, the normal, everyday radiant heat is going to easily reach 140 or 150 degrees at the ceiling.
So the standard sprinkler would activate constantly just from the normal manufacturing process.
Precisely. You'd have catastrophic accidental discharges of water into a blast furnace, which would cause a massive steam explosion.
That makes perfect sense. You match the sensor to the baseline environment. Okay, let's break down the four primary types of sprinkler piping systems: wet pipe, dry pipe, Preaction, and Deluge. Let's start with the baseline, the wet pipe system.
The wet pipe system is the simplest and most reliable. The piping network is completely filled with water under pressure at all times, right up to the closed sprinkler heads.
So delivery is instantaneous.
Yes. When a fire breaks out, the bulb shatters, and water discharges immediately.
If the pipes are full of water all the time, the obvious Achilles heel is ambient temperature, right?
Exactly. Freezing. You cannot use a wet pipe system in an unheated warehouse in Chicago in January.
Because the pipes will freeze and burst.
Right. And when the ice eventually thaws, the municipal water supply just pumps thousands of gallons of water through the broken pipes, destroying the facility.
Which naturally leads us to the engineering solution for freezing environments: the dry pipe system.
Explain the mechanics of this, because it's more complex than just emptying the pipes.
Right, so a dry pipe system is specifically designed for freezing temperatures. The vast network of overhead pipes isn't filled with water. It's filled with pressurized air or nitrogen.
So what holds the municipal water back?
Down in a heated, insulated riser room, there's a specialized device called a dry pipe clapper valve. Below the valve is the pressurized municipal water. Above the valve is the pressurized air in the pipes.
But how does air pressure hold back massive water pressure? Water is much heavier.
It relies on surface area differentials. The design of the clapper valve exposes a much larger surface area to the air side than the water side, usually about a 6-to-1 ratio.
Oh, clever.
Yeah, so a relatively low air pressure, like 40 psi, can successfully hold back a much higher water pressure of 100 psi.
So what happens when a fire starts in the warehouse? The heat melts the fusible link. But instead of water coming out, the pressurized air rushes out of the open head. As the air escapes, the air pressure inside the pipes drops rapidly.
And that breaks the balance of the clapper valve.
Exactly. The massive water pressure pushes the valve open, rushes into the piping network, travels to the open sprinkler head, and discharges onto the fire.
Okay, I am going to push back on this design logic a bit.
Sure.
If the wet pipe system is instantaneous, why are we accepting the massive delay of a dry pipe system? The air has to bleed out, the valve has to trip, the water has to travel through hundreds of feet of empty pipe. NFPA says water has to reach the furthest head within 60 seconds. But in a fast-moving fire, 60 seconds is an eternity. Isn't speed the most critical factor?
Speed is absolutely critical, but safety engineering is an exercise in balancing competing risks. The delay in a dry pipe system is a calculated trade-off.
So you're accepting a slower response time to eliminate the risk of a burst pipe.
Exactly. Yes, because of that 60-second delay, the fire will likely grow a bit larger. You might have 4 or 5 sprinkler heads pop open instead of just 1 or 2.
So you get more fire damage and more water damage.
True, but it is vastly superior to having a frozen, ruptured pipe providing absolutely zero fire protection when the building burns to the ground.
That's a very fair point.
Oh.
Let's move to the third type, which seems to take the dry pipe concept and make it even more complex. The preaction system.
A preaction system is a highly specialized hybrid. Like a dry pipe system, the overhead pipes are normally filled with air. However, the valve holding the water back is not tripped just by a drop in air pressure.
Oh.
No, the valve is tied electronically to a completely separate fire detection system like smoke detectors.
I want to make sure I understand this because it sounds like a 2-factor authentication process for a sprinkler. You need 2 separate events to occur to get water on the fire.
That is a brilliant analogy. It is exactly like 2-factor authentication. Let's walk through it. Step 1. A smoke detector on the ceiling senses a fire. It sends a signal to electronically open the main water valve in the riser room.
So the valve opens and water rushes into the overhead pipes.
Yes. The system has effectively just converted itself into a wet pipe system. But, and this is crucial, no water is flowing out of the sprinkler heads yet.
Because the physical sprinkler heads are still intact.
Correct. Step 2. The fire must continue to grow, generate enough heat to reach the set temperature, and physically melt the glass bulb on the specific sprinkler head. Only then does the water actually discharge.
Why build a system that requires 2 totally independent triggers? Why make it so complicated?
It's all about preventing accidental water discharge in highly sensitive environments. Imagine a multi-million-dollar data center housing critical servers, or a museum vault with priceless artifacts.
Right, environments where water damage is just as catastrophic as fire damage.
Exactly. Let's say you have a basic wet pipe system in that data center. A maintenance worker on a ladder accidentally swings a wrench and knocks the glass bulb off a sprinkler head.
Oh no. Hundreds of gallons of black water blast all over the servers.
Total loss. But if they knock the head off in a preaction system,
What happens?
the pressurized supervisory air in the pipe escapes. The system triggers a trouble alarm at the panel, alerting maintenance that a pipe is breached. But the water valve in the riser room does not open.
Because the smoke detectors haven't sensed any smoke. The 2-factor authentication failed.
Precisely. So the room stays dry. It's a fail-safe mechanism to buy time for human intervention.
That is incredibly smart engineering. Now, the final type of water system is the deluge system. And this one fundamentally breaks the rule we established earlier about individual sprinkler heads, right?
It does. In a deluge system, all the sprinkler heads on the piping network are permanently open. They don't have glass bulbs, they're just open brass nozzles.
So if they're open to the room, the pipes must be dry.
Yes, completely empty. The system relies entirely on a separate, highly sensitive fire detection network, like UV flame detectors. When the sensors spot a fire, they send an immediate signal to the main deluge valve.
And when that valve opens,
A massive volume of water rushes in and pours out of every single sprinkler head simultaneously. It instantly floods the entire protected area with a torrential downpour.
that sounds incredibly destructive. When would you ever intentionally design a system to flood an entire facility?
You design a deluge system when the hazard is so volatile and the fire growth potential is so rapid that you simply cannot afford to wait 60 seconds for individual thermal heads to pop.
Give me an example.
Think about a massive aircraft hangar housing jets full of aviation fuel. If a fuel line ruptures and ignites, the fire can spread across a massive pool of jet fuel in milliseconds.
Right.
A deluge system acts as a massive instant water curtain. It suppresses the flames, prevents radiant heat from igniting adjacent aircraft, and cools the structural steel of the roof so it doesn't collapse. It's a brute force approach for extreme hazards.
That really drives home the idea that fire protection is custom-tailored to the chemistry of the threat. You don't put a deluge system in a server room, and you don't put a Preaction system in a munitions plant.
Exactly.
Let's ground this theory in a practical scenario from the sources. The Bowen EHS prep materials have a fascinating question about system dynamics. It goes like this. A well-maintained fire suppression system uses wet pipe sprinklers in an office building. The sprinklers activate at 100 degrees. There's a drop-down acoustic ceiling, but many of the ceiling panels have been removed by a maintenance crew. How is the removal of the ceiling panels likely to affect the sprinkler head operation? The options are basically respond more quickly, more slowly, or remain unaffected.
This is a classic application of applied fire physics. The correct answer is that the sprinklers are likely to respond significantly more slowly.
I want you to break down the physics there, because my layman's instinct might be that without those acoustic panels blocking the way, the heat would just shoot straight up to the sprinklers and activate them faster.
It's a common misconception, but it's entirely about convective heat transfer. When a fire starts, the hot combustion gases rise in a vertical column called a fire plume. If you have a solid, flat ceiling, those hot gases travel up, hit the ceiling, and are forced to spread out horizontally in what we call a ceiling jet.
So the heat mushrooms out and banks against the ceiling barrier.
Yes, rapidly raising the temperature right where the sprinkler heads are located. The thermal element reaches 100 degrees quickly and activates.
Oh, I see where this is going.
But if you remove those ceiling panels, the hot gases don't hit a wall. They continue rising straight up through the hole, up into the massive open plenum space between the drop ceiling and the actual structural roof deck.
The heat escapes into the attic space.
Exactly. Because the heat isn't banking against the drop ceiling where the sprinkler is located, the air temperature around the sprinkler stays cool for much longer. It takes a vastly larger fire to eventually fill up that entire upper space and push the hot air down to the sprinkler head.
That is a phenomenal example of how minor, seemingly harmless facility maintenance issues, like leaving a few ceiling tiles out, can completely cripple a $1 million engineered safety system.
Precisely. You can design the best system in the world, but if the facility geometry changes, the system fails.
Which is a perfect transition. Water is an incredible tool, but as we noted with data centers and combustible metals, it's not always the right tool. Let's move from water-based systems to special hazard and chemical suppression systems. We're talking primarily about Class B and Class C fires. Let's start with carbon dioxide or CO2 systems. How did these differ from sprinklers?
Well, carbon dioxide extinguishes fires primarily by physically displacing the oxygen in the environment. These systems store liquid CO2 in high-pressure cylinders. They can be engineered for total flooding, where they literally fill an entire enclosed room with CO2 gas, or local application, where they discharge directly onto a specific piece of equipment.
But there is a massive inherent life safety contradiction here, right? If the goal of safety is to protect human life, dumping a room full of CO2 seems counterproductive.
It is a very severe life safety hazard. CO2 is an asphyxiant gas. By design, a total flooding CO2 system is engineered to reduce the ambient oxygen concentration from the normal 20.9% down to below 15% to kill the fire.
Where human beings need about 19.5% oxygen to maintain normal cognitive function.
Exactly. If a CO2 system discharges while workers are inside, the oxygen level plummets instantly. It poses a lethal, toxic, and suffocation hazard. People will pass out in seconds.
That's terrifying.
And furthermore, the physical discharge is incredibly violent. It creates a deafening roar that can exceed 100 decibels, and the rapid cooling creates a dense white fog of dry ice snow that drops visibility to zero. It causes massive panic.
So if the system is that dangerous, how do safety engineers mitigate that risk? You can't just hope nobody is in the room.
You rely on strict engineering controls. Any CO2 system installed in an occupied space absolutely requires pre-discharge alarms. These are blaring sirens and strobe lights that trigger the moment smoke is detected. The system has a built-in time delay, usually 30 to 60 seconds, giving workers time to evacuate before the gas dumps.
And what if maintenance workers are in there servicing the equipment?
That's where mechanical lockout switches come in. Before personnel enter a CO2-protected space, they must physically turn a lockout valve that mechanically prevents the cylinders from discharging, even if the fire alarm panel commands them to.
That makes total sense. Okay, next up on the chemical side, halons.
Halons were considered the absolute wonder drug of fire suppression for the latter half of the 20th century.
What made them so magical?
They attack that elusive fourth leg of the fire tetrahedron. When halon gas hits the heat of a fire, it releases bromine or chlorine atoms. These atoms aggressively seek out and bond with those highly reactive hydroxyl radicals we talked about earlier. They chemically interrupt the chain reaction, killing the fire almost instantly.
And from a facility management standpoint, their big selling point was that they leave zero residue, right?
It was revolutionary. You could have a fire in a room full of mainframe computers. The halon system would put out the fire in seconds and you just ventilate the gas out. The computers would still be running perfectly, no water damage, no corrosive powder.
But as with all winter drugs, there is a massive catch.
2 catches. First, when halon is exposed to the extreme thermal energy of the flames, it decomposes into highly toxic byproducts, like hydrogen fluoride gas, which is dangerous to breathe.
And the second catch, the global one.
The environmental impact. Halons are incredibly potent ozone-depleting substances. Because of this massive environmental threat, the production of new halon was completely phased out globally under the 1987 Montreal Protocol.
So if I'm building a brand new data center today, I can't buy halon. What has the industry developed to replace it?
The industry shifted to clean agents. There are 2 main categories now. First, inert gases like argon or nitrogen. These work by lowering the oxygen concentration, but they're much safer for human exposure than CO2.
And the second category?
Synthetic halocarbon agents like FM200 or fluorinated ketones like Novec 1230. These are chemically engineered to mimic halon. They put out the fire rapidly, leave zero residue, but they're designed with an ozone depletion potential of exactly 0.
Let's do a thought experiment. Imagine you're a safety candidate and you're tasked with designing fire suppression for 2 entirely different facilities. A highly sensitive telecommunications server room and an open-air jet engine testing hangar. How do you evaluate the trade-offs?
That evaluation is the core essence of fire protection engineering. For the server room, the business continuity risk is massive. Water damage would destroy the servers. So your primary defense should be a total flooding clean agent system, like Novec 1230. It puts the fire out in seconds, leaves 0 residue, and is totally safe for the IT staff.
And the jet engine hangar?
Completely different hazard profile. It's a massive drafty structure with huge quantities of Class B flammable aviation fuel. A clean agent gas would be utterly useless here. The massive volume and drafty doors mean the gas would just blow away.
And water sprinklers alone might just spread the burning pool of jet fuel.
Right. In this environment, you need foam.
I want to dive into foam. The sources mentioned foam can expand anywhere from 100 to 1,000 times its original liquid volume. How does a liquid do that?
Foam is basically a mass of gas-filled bubbles formed from water and a chemical concentrate. When it hits a nozzle, ambient air is introduced, agitating it and blowing it up into bubbles, much like putting dish soap in a running sink.
And how does it kill a massive Class B fire?
Its primary mechanism is physical smothering and vapor sealing. When you apply foam to a massive burning liquid fuel spill, it flows across the surface of the fuel. It physically separates the flames from the fuel source.
Ah, I see.
But more importantly, it forms a microscopic aqueous film over the fuel. This film completely suppresses the release of flammable vapors. If there are no vapors rising, there is absolutely nothing for the fire to burn.
That's brilliant. What's the functional difference between low expansion and high expansion foam?
Low expansion foam has a relatively dense, wet consistency. It expands maybe 10 to 20 times its volume. Because it's heavy, it's excellent for shooting out of a high-pressure nozzle across a long distance, like at an airport.
Yeah, high expansion.
High expansion foam can expand up to 1,000 times its liquid volume. It doesn't look like liquid. It looks like a towering, moving wall of incredibly light soap suds.
1,000 times, wow.
Yeah. You use it to completely fill massive, inaccessible, 3-dimensional volumes, like a deep coal mine shaft or an underground cable vault. It flows around obstacles and suffocates the fire in all 3 dimensions.
What about dry chemical systems? Where do they fit in?
Dry chemical systems utilize very fine pressurized powders. They knock down Class B and C fires incredibly fast by smothering, cooling, and acting as a physical shield between the liquid fuel and the radiant heat of the flames.
But they must make a massive mess, right?
An incredible pervasive mess. The fine powder gets into every crack, and many are highly corrosive to metals. You would never intentionally use a dry chemical system on sensitive electronics.
One more automated system mentioned in the sources, water spray or water mist systems. They seem to bridge the gap between water and gas.
Water mist technology is a huge innovation. By utilizing extremely high-pressure pumps and specialized micronozzles, these systems atomize liquid water into microscopic droplets.
What's the advantage of making the droplets so tiny?
It vastly increases the total surface area of the water relative to its volume. That massive surface area maximizes the water's ability to absorb heat. As the fire's heat turns those billions of microdroplets into steam, it rapidly cools the air and dilutes the oxygen.
So it's mimicking a clean agent gas system.
Yes, but without the toxic asphyxiation hazards of CO2 or the environmental concerns of chemical agents. Plus, it uses significantly less water than a traditional sprinkler system, meaning far less collateral damage.
Okay, we've spent a lot of time on automated systems. Let's pivot to manual suppression and the maintenance required to keep all of these systems functional. This brings us to portable fire extinguishers. They are hanging on the wall in every building in America, but there are very strict rules governing them.
Yes. Portable fire extinguishers are intended strictly as a first line of defense to be used by trained workers to handle fires only during that critical incipient stage.
Right.
They are not designed to fight a raging structural fire. Their placement and maintenance are heavily regulated by OSHA standards and NFPA 10.
Let's look at the specific OSHA rules for the construction industry. What exactly does OSHA mandate?
OSHA requires employers to provide a fire extinguisher rated not less than 2A for every 3,000 square feet of protected building area, and critically, the maximum travel distance from any point to the nearest fire extinguisher must not exceed 100 feet.
Let me stop you and push back on this regulatory logic.
Well, go ahead.
We just spent 40 minutes talking about these incredibly sophisticated automated systems. We engineer these systems so humans don't have to fight the fire. So why does OSHA care so deeply about whether a manual extinguisher is exactly 100 feet away versus 125 feet away? Are we really expecting untrained employees to play firefighter against a massive industrial blaze?
That is a fantastic question. The answer cuts right to the heart of fire dynamics. First, no. OSHA emphatically does not want untrained employees fighting fires. If an employer expects employees to use extinguishers, they must provide hands-on training annually. If they don't, the policy must be evacuate immediately.
Okay, so assuming they are trained, why the strict 100-foot rule?
It's tied to the physics of the incipient stage. Fire growth is not linear, it is exponential. A fire can literally double in size every 30 to 60 seconds.
So it's a race against exponential math.
Exactly. Let's translate that 100 feet into time. If a worker spots a small fire in a trash can and they have to run 150 feet down a hallway, navigate around pallets to grab the extinguisher, figure out the pin, and run 150 feet back. A solid 60 to 90 seconds have elapsed.
And in 90 seconds.
That small trash can fire has likely ignited the curtains and the ceiling tiles. It has transitioned from the incipient stage into the free-burning stage. The radiant heat is now too intense to approach.
Attempting to fight it with a 10-pound extinguisher is deadly at that point.
Right. The 100-foot rule exists so that if a trained worker decides to fight the fire, they can physically reach the tool and return while the fire is still small enough to be safely conquered.
It's a biological and physical time limit based on combustion curves. That is fascinating.
Yep.
But just having the extinguisher on the wall isn't enough. It has to actually function. Let's break down the inspection timeline. We have monthly, annual, and hydrostatic testing.
The monthly inspection is essentially a visual quick check. You're looking to verify readiness.
What exactly are they looking for?
You check that it's in its designated place. You verify it's easily accessible, meaning a forklift driver hasn't stacked boxes in front of it. You check the pressure gauge to ensure the needle is in the green zone. You check that the metal pull pin is in place and the plastic tamper seal is unbroken.
Simple enough. What about the annual maintenance?
That's a deep dive mechanical inspection, almost always performed by a certified outside contractor. They take it off the wall, examine all the mechanical parts, the valve assembly, and potentially empty and refill the agent.
And the final, most intensive level is hydrostatic testing at 5 or 12 years. What exactly is a hydrostatic test and why is it necessary?
A fire extinguisher is a pressurized metal vessel holding gas at hundreds of pounds of pressure, 247. Over time, metallurgical fatigue or internal corrosion can severely compromise the structural integrity of that metal cylinder.
And if the cylinder is compromised, it becomes a bomb when you try to use it.
Exactly. When you squeeze the handle, the internal pressure shifts and the entire cylinder can rupture explosively in your hands. Hydrostatic testing verifies the shell's structural integrity.
Do they just pump it full of high-pressure air and see if it explodes?
No. If the cylinder ruptures under air pressure, the rapid expansion of the compressed air creates a deadly explosion. That is why they use water, hence hydrostatic. water is incompressible.
So fill it with water, pump it past its normal operating pressure, and see if the metal stretches.
Precisely. If the metal expands past its elastic limit and permanently deforms, or if it leaks, the cylinder fails and is destroyed.
Wow. So we have a rigorous inspection regimen for manual tools, but we also have to rigorously inspect the massive automated systems. Having $1 million Preaction sprinkler system is completely useless if a valve is rusted shut.
This is where we bridge into OSHA's Process Safety Management, or PSM, standard 1910.119, specifically mechanical integrity. That absolutely includes the fire suppression pumps and deluge systems protecting hazardous chemical processes.
The sources mention that inspections must follow recognized and generally accepted good engineering practices, or ragged cheap. What does that actually look like for a fire system?
A huge part of this is looking for subtle creeping degradation. For example, the engineering manuals discuss a pervasive phenomenon called loading.
What exactly is loading?
Loading is the slow accumulation of foreign materials directly onto the sprinkler heads. Think about a woodworking shop generating fine sawdust, or an auto body shop where overspray from paint slowly drifts up to the ceiling.
Oh, wow. The sprinkler head just gets coated in a layer of grime. Why is that a critical failure point?
Because that layer of dust or paint acts as thermal insulation. It physically insulates the heat-sensitive glass bulb from the ambient air.
So it drastically increases the thermal lag we discussed earlier.
Yes. If a fire breaks out, the air temperature might reach 160 degrees, which should easily activate a 135-degree head. But the thermal element is insulated by paint. It doesn't feel the heat, so it doesn't melt.
And the fire just keeps growing.
Exactly. Routine visual inspections are designed specifically to catch loading. And if a head is loaded, you don't try to clean it and risk breaking the bulb. You replace the head entirely.
That makes perfect sense.
I agree.
Let's talk about the operational reality of taking a massive sprinkler system offline for maintenance. A facility manager can't just shut the main water valve off and go to lunch, right?
Absolutely not. Disabling a fire protection system creates a severe vulnerability known as a system impairment. There are strict protocols. First, you must formally notify the local fire department and your corporate insurance carrier.
Because if a fire happens, the fire department needs to know they are walking into an unprotected building.
Yeah, precisely. They alter their response strategy immediately. Second, you must minimize the downtime by scheduling work during off hours. And third, you must implement alternative protections, like a continuous fire watch.
Where trained personnel patrol the area with extinguishers.
Yes. Their sole job is to watch for sparks or smoke and suppress a fire instantly.
Which ties perfectly back into another core process safety management concept, management of change, or MOC.
Yes, MOC is arguably one of the most critical functions of a safety engineer. Facilities are not static.
Give me a practical example of how MOC applies to fire suppression.
Let's say your company takes a storage room that has been storing cardboard boxes for years and decides to convert it into a chemical mixing room for highly flammable solvents.
You're fundamentally changing the chemistry of the fuel load.
Exactly. You're changing from a Class A hazard to a severe Class B hazard. A rigorous MOC review process ensures a safety engineer asks, is the existing wet pipe sprinkler system still adequate?
And the answer would likely be no, because water on a solvent fire might spread it.
Right. You might have to install a localized high-expansion foam system before you allow the new process to begin.
That really illustrates the beauty of safety engineering. It isn't just a list of unrelated rules. The specific molecular chemistry of the fuel dictates the extinguishing agent. The physical geometry dictates the sensor. The physiological limits of human running speed dictate the travel distance to the manual extinguisher. It's a deeply interconnected web.
And that profound interconnectedness is exactly what the ASP and CSDA exams are designed to test. They're testing if you possess the critical thinking skills to understand how a subtle failure, like a painted-over sprinkler head, can put hundreds of lives at risk.
Okay, let's pull all of this dense material together for a final summary for our listeners on this Domain 4, Topic 7 deep dive, or rather today's QHSE Talks. What are the core takeaways?
First, deeply understand the chemistry of the fire tetrahedron and the classes of fire. You must be able to match the fuel hazard flawlessly to the correct extinguishing agent. Second, know the mechanical differences between wet pipe, dry pipe, Preaction, and Deluge sprinkler systems. Third, comprehend the severe human hazards of alternative chemical agents, like the lethal asphyxiation risk of CO2. And finally, internalize your OSHA portable extinguisher spacing requirements and strict inspection timelines.
It all comes down to relentless vigilance, designing the right system based on sound physics and maintaining the administrative discipline to ensure it actually works. But before we sign off, I want to look forward. The physical world is changing rapidly. What is the next frontier for fire protection engineering?
That is the perfect, provocative question to leave our listeners pondering. As our built environment rapidly evolves for the global energy transition, we are introducing massive, unprecedented hazards.
Like what?
Think about the proliferation of gigawatt-scale lithium-ion battery energy storage systems. When a massive lithium-ion battery goes into thermal runaway, it doesn't behave like a normal fire. It produces its own oxygen internally as the cathode breaks down.
Wait, really? So you literally cannot smother it with CO2 or foam because it doesn't even need ambient air to burn?
Exactly, and it generates extreme heat that can reignite the battery cells days after the initial fire is seemingly extinguished.
Whoa.
The traditional fires of tomorrow might not be easily categorized into the neat A, B, C, or D boxes we use today.
So the ultimate question is, are our current legacy suppression technologies truly ready for the energy transition?
It is a critical vulnerability. As safety professionals, we have to ask ourselves continuously, how will our dynamic industrial defense systems need to adapt and evolve to fight these new, complex synthetic hazards?
A brilliant and slightly terrifying thought to end on. Because fire protection isn't a static wall you can just build and forget. It is a living, adapting system, and it is up to the safety professional to ensure that system is always one step ahead of the threat. Thank you for joining this edition of QHSE Talks. We wish you the absolute best of luck on your exam preparation, and more importantly, in your everyday mission to keep your workplaces and your people safe.